Good afternoon, boys and girls. Welcome to another session of Technical Sciences, grade 12. Today we are doing work, energy, and power, and it's a question and answer session. Right? If it is your first time tuning, my name is Mr. Spius Banyoni, and I will be taking you through the lesson for today. Now, you will remember, my dear learners, that we have worked on work, energy, as well as power throughout the week. And today, I was expecting that some of you would be sending questions through so that I'm able to answer them and give you some clarity on concepts that you perhaps may not have understood. But nevertheless, always ready for you, and I have questions that I have prepared for you, and we are going to work through them. Right. So, in our overview, I'm going to remind you of the important terms and definitions in this topic. Again, I will be reminding you of the important formulae as well as constant values that you get on your data sheet. Then we'll be doing questions on work, energy, and power. And lastly, just how many marks this topic is going to be at the end of the year, as well as in your preparatory examinations. Now, my dear learners, you must know how to define the following. You must be able to define the term work. And we say work is the product of the applied force on an object and the displacement in the direction of the force. It is the product of the applied force on an object and the displacement in the direction of the force. Remember, my dear learners, why are we saying work is the product? Because we take the value of the applied force and we multiply it with the value of the displacement, and hence we talk about the product. Then you must be able to define the term energy. And energy, we define it as the ability to do work. It is the ability to do work. Furthermore, my dear learners, these definitions that are following here, they are not necessarily in your examination guidelines, but we will be asking you questions and we will be expecting you to be able to explain what kinetic energy is, what potential energy is, and also what mechanical energy is. And therefore, you must be able to actually have a good idea of what are we talking about when you talk about those forms of energies. And when you talk about kinetic energy, remember, we are talking about the energy an object possesses because of its motion. So when an object is moving, we know that the object will have kinetic energy. And why does the object have kinetic energy? Because the object has a particular speed. Then the potential energy, remember, that is the energy that an object possesses because of its position from the surface of the earth. So it is the energy an object possesses because of its position from the surface of the earth. So you will remember that if an object is right on the ground, then that particular object, its gravitational potential energy will be 0 joules, and when the object is somewhere above the ground, then the height will be greater than 0, and if the height is greater than 0, then the object will have a gravitational potential energy. And very important, my dear learners, it is gravitational potential energy. Then we talk about mechanical energy, and we say mechanical energy is the sum of the gravitational potential energy and kinetic energy of an object. So it is the sum of the gravitational potential energy and kinetic energy of an object. Right. Then we must be able to state the principle of conservation of mechanical energy. And that principle stated, it says, the total mechanical energy in an isolated system remains constant. In other words, put somewhat differently, we can say the total mechanical energy in an isolated system is conserved. So my dear learners, you need to remember that. Are we clear? So in brackets, you don't have to include it. This is just a reminder of what mechanical energy is, which is the sum of the gravitational potential energy and the kinetic energy of the object. Again, what we did in term 1 and what you need to remember again is to define an isolated system. And we know that an isolated system is a system whereby the net external force acting on the system is 0. So the net external force acting on the system is a 0. And lastly, we must be able to define power. And we say power is the rate at which work is done. Or another person or another learner can say power is the rate at which energy is expended. Right, so very critical definitions that you need to know because they are all important. And remember, most of the time when we start a question, we ask you to give us definitions that are going to be relevant, especially for the calculations that you will be doing, as well as the principles. Again, remember, definitions and principles, they make up 40% of your question paper. So if you are really good with your definitions, you can really do well in technical sciences. Right. Then let us talk about the important formulae. So when you go to your formula sheet, these are the formulas that you are going to get. The first formula there is the formula that we use to calculate work. And we say work is equal to the force multiplied by the displacement multiplied by the cos of theta. Remember, the force there could be the force in question. So if you are talking about the force of gravity and you want to calculate the work done by the force of gravity, it simply means the magnitude of the force that you will substitute there will be the force of gravity. If you want to calculate the work done by the frictional force, then the value that is going to be substituted there will be the value of the frictional force. If you want the work done by the applied force, the force that you are going to apply there will be the frictional force. Are we together? Right. So it will be the frictional force. So it just depends what you want to calculate. So the work that you want to calculate will definitely depend on the force in question, and you will substitute that accordingly. Then this formula is the formula to calculate the kinetic energy. Remember now, the symbol for kinetic energy is equal to half mv squared. It's equal to half mv squared. And kinetic energy, we represent it by a capital letter K. And it will be equal to half mv squared. And we know the m there represents the mass in kilograms, and v there represents the speed in meters per second, and you square it. Or EK is equal to half mv squared. So EK is another symbol that we use for kinetic energy. We know the E there is for energy and the K is for kinetic. Then the formula that we use for mechanical energy, we say mechanical energy is equal to kinetic energy plus gravitational potential energy. So that's energy, but it's mechanical. That's energy, it's kinetic. That's energy, it's potential energy. Another symbol that we use for mechanical energy, remember, it's E with the subscript M. That means mechanical energy. Then this formula relates to power. So the average power is equal to the force multiplied by the average speed. Now, let us say, for example, you have a crane, and a crane is lifting a block of mass 2 kilograms, right? And let's say that is some cement that needs to go upstairs. Now, if you want the power of that particular crane, you will use this formula. And then for the force, you will substitute the force that the crane is applying to that block of the mass that is going upwards. But here, you will substitute the speed with which the object is moving, that block of mass. So this will be the force of the crane, but this will be the speed with which the block of mass is going upwards. Then you come to this formula. This formula is a formula that we use to calculate gravitational potential energy. And we say U is equal to mgh. So the U there, my dear learners, represents gravitational potential energy. And it will be equal to the mass, which is measured in kilograms, the G, which is gravitational acceleration, measured in meters per second squared. And we know that this value, you are going to get it on your data sheet. It's a constant value. And then the height will be the height above the surface of the earth, or the height above the ground. If the object is on the ground, my dear learners, there you are going to substitute 0. Or you can use this formula. The only difference is that here we are representing our gravitational potential energy as EP. Right. Then we go to this formula. Now we know K represents kinetic energy and the delta means the change. In other words, this formula is the formula that we use to calculate the change in kinetic energy. And the change in kinetic energy will be equal to the final kinetic energy minus the initial kinetic energy. So if you want to calculate the change in kinetic energy, it will be equal to the final kinetic energy of the object minus the initial kinetic energy. My dear learners, you will remember when we say final kinetic energy, we are basically talking about the kinetic energy at the end of the motion, and the initial kinetic energy will be the kinetic energy at the beginning of the motion. Or delta EK, which means the change in kinetic energy will be equal to final kinetic energy minus initial kinetic energy. So this is actually the same thing. It's just that on this formula, we are representing kinetic energy as a capital letter K. And there we are representing kinetic energy as energy with subscript K for kinetic. And then this is another formula that we use to calculate power. And by definition, remember, we say power is the rate at which work is done. And hence, this is W divided by delta T. In other words, if I wanted to calculate, like in the previous example, a crane that is lifting a block of mass, maybe it is cement that needs to go upstairs. So the lifting force is doing some work. So you will calculate the work done by that lifting force, and then you will determine the time with which the work was done, meaning the time with which the lifting took place. So be able to use this formulae. Furthermore, my dear learners, these formulae are the formulae that are relevant when the question asks you to use energy principles only. So if we say use energy principles, for example, to calculate the speed of the object at the end of a motion, it means the formulas that are going to be relevant for you as these ones. If you use any other formulas, it means you are using formulas that are not energy principles. And if they are not energy principles, then we cannot award you marks. So if we want you to use energy principles, these are all the formulas that you need to use. Right, so very important. Right, then you are going to get a table. That is table 1. It's a table of physical constants. Now this table will give you the acceleration due to gravity. And the symbol for that is a G. And that is 9.8 meters per second squared. So this value, my dear learners, always go back and check it where you see that a formula requires G. Go back to your data sheet and see which constant you have. And when you have the constant, you can see that, oh, amongst this constant, I have a G, and then the value of G is 9.8, and the units there are meters per second squared. So my dear learners, that's a formula that you then use as you perform your calculations. For example, in this formula, you can actually use it because this formula for gravitational potential energy will require you to calculate the value for G. So be able to work with that. Right. Now, I want us to work on this particular question. This question was sourced from a technical sciences control test in the Free State in March 2018. Right, remember this is a question and answer session, and I want us to actually be able to interact and to help you really get the concept through in terms of what work, energy, and power is about. The question reads as follows. A stone of mass 2 kilograms is dropped. Now, when we say it is dropped, what does that mean? It tells me that at the point where it left, its speed is 0 meters per second. Why? Because it is being dropped. It is not thrown downwards. So if we drop it, then the speed when it is dropped is an initial speed of 0 meters per second. From a height of 50 meters. Ignore air resistance. Now, if we are required to ignore air resistance, what does that statement in particular tell us? This statement tells us that we must take the system to be isolated. We must assume that our system is isolated. And we know when we take the system to be isolated, there are quite a number of principles that we can apply, and there's quite a lot of information in that. Are we together? Then, question 5.3.1, it says, give the principle of conservation of mechanical energy in words. And very critical, my dear learners, they are saying you must give it in words. Now, if we say you must give it in words, it means you can't give us in a formula, because Those are some of the mistakes that we see at the end of the year when we mark you. You find that another learner will say EM at the top is equal to EM bottom, and then the learner expects to get 2 marks. You cannot get 2 marks, my dear learners, because you did not say it in weights. Now, the principle of conservation of mechanical energy, it simply states the total mechanical energy of an isolated system is conserved. Or another learner can say the total mechanical energy of an isolated system remains constant. Are we together, my dear learners? Right. Let's see how we mark this particular principle. You can see there it says the total mechanical energy in an isolated system remains constant. So this is 2 marks or nothing. In other words, my dear learners, it means if you omit critical words there, then you are going to get a 0 altogether. It means everything has to be there. So it's not part marking. We are not saying, okay, the learner said the total mechanical energy in an isolated system, let us award 1 mark, and then remains constant, let us award 1 mark. Everything has to be correct, so you get 2 marks or 0. And hence, I prefer to then give you the marking guidelines so that you are able to see how we mark you, because if you don't see how we mark you, some of the learners would then take things for granted or know your definitions partially, and then you end up forfeiting marks. So we actually want to help you, right? Then before we even go further to the questions, they said to us it is being dropped. So it means the height from where it was dropped is 50 meters. It means the 50 meters is from this position up to that particular position. So that gives you 50 meters. Now, we are required to calculate the gravitational potential energy of the stone at the height of 50 meters. In other words, we are being asked to calculate the gravitational potential energy when the object is at this particular point. So we want the gravitational potential energy at this point, right? Now, we know gravitational potential energy depends on the height of the object. And we also know that the height of the object is directly proportional to the gravitational potential energy. So to calculate the gravitational potential energy, they are giving us 3 marks. Now, how do we calculate the gravitational potential energy? We will write there EP is equal to mgh. This is gravitational potential energy. It is equal to mgh, right? So that carries 1 mark. Then the mass is 2 kilograms. The G, which is a constant value that you get from your data sheet, it's 9,8. And the height from where it was dropped, when it was 50 meters above the ground, is 50. And that entire substitution, everything must be correctly substituted, then you will get a mark. And this will be equal to 980 joules. And that will be your 3rd mark. Remember, the 3rd mark is for the correct magnitude with the correct unit. And remember, we said a joule is a capital letter J. So that gives us the 3 marks. Then the next question says, calculate the gravitational potential energy of the stone after it has fallen a distance of 40 meters. So now we want to know what is the gravitational potential energy of the stone when it has fallen a distance of 40 meters. So let us take it from here. Now it falls downwards. It falls downwards. And let us say up to there. It is the 40 meters. In other words, our stone, there is our stone. Our stone is at that particular point. Now, we know here it is the ground, right? This is the ground. Now, if it is the ground, remember how we measure the height. The height is measured from the ground to where the object is. And that particular displacement now, we are going to know, or rather, that particular height is definitely going to be 10 meters. How do we know that the height is 10 meters? Remember, it started 50 meters above the ground. So it fell for 40 meters. It means it is now 10 meters above the ground. And the height there will be 10 meters because we measure from the ground to where the object is. So how do we calculate that? Remember, it's gravitational potential energy. So EP is equal to mgh. Then the mass of the stone, it's still 2 kilograms. The gravitational acceleration is 9.8. And now the height above the ground is 10 meters. So you do your calculations, you get 196 joules. So where are the marks allocated? They are allocated on the substitution, and they are also allocated on the final answer with the correct magnitude as well as the unit. But remember, my dear learners, we will not mark this substitution if the formula is not there. So the formula must, it's a must that is there. Otherwise, we cannot mark your substitution altogether. So it is very critical that you are able to give us a formula because we need to know how this particular substitution took place. And most of the time, actually, we will be awarding a mark for the formula. It's just in this particular case, no mark was awarded for the formula. But you can see from 5.3.2, a mark was allocated for the formula. Right. Then let us go to question 5.3.4. And we are required to calculate the speed of the stone after it has fallen 40 meters. Now, when it has fallen 40 meters, remember that is when the object is here. So we are being asked to calculate the speed of the object when it is at that particular point. Now, my dear learners, how are we going to do that? Now, for us to be able to do that, we then need to check or perhaps understand that as it was falling, when it has fallen 40 meters and it's at that point, the object actually has not stopped. So it is still moving. So we need to know what is the speed at that point. And we are definitely sure that the speed is not zero. Why? Because the object is still in motion. It was still going downwards. Now, what we can think of is we have been told to ignore a resistance. In other words, the system is isolated. In other words, the mechanical energy at the top is exactly equal to the mechanical energy at the bottom. It's exactly equal to the mechanical energy at any point where this object is moving. So the value for mechanical energy is the same here, there, here, there, anywhere where the object is moving. So the mechanical energy at the top, which is at this point, is exactly equal to the mechanical energy at that particular point when it has fallen 40 meters. It's exactly equal to the mechanical energy when it's at the ground. So we could still apply the principle of conservation of mechanical energy. And that is the one that is even simpler for you, where we say the mechanical energy at A, which is the top, is equal to the mechanical energy at B, and B represents a point where the object had already fallen 40 meters altogether. Then we say, okay, mechanical energy is the sum of the gravitational potential energy and the kinetic energy of an object. And hence we added the gravitational potential energy, which is mgh, to the kinetic energy, which is half mv squared, which is at point A, which we regard as the top. And then again, mechanical energy is still the sum of the gravitational potential energy and the kinetic energy at point B, and point B we know that is when it had already fallen 40 meters from the top. In other words, point B we can actually represent it as the bottom, meaning we can take that particular position as the bottom, right? Then if you do your substitution for the top, for gravitational potential energy, you get a value of 980. Remember, we got it there. At the top, remember the mass was 2, the gravitational energy acceleration was 9.8, and the height was 50. So all of that at the top gave us 980. And hence there we have 980. Plus, the kinetic energy at the top is 0. Why is it 0? Because the speed at the top is what? Is 0. Why are we saying it is 0? Because they told us that the stone is being dropped. So when you say half multiplied by 2 multiplied by the speed of 0 squared, you get a value of 0. It is equal to, at the bottom, remember, that's when it had fallen 40 meters from the top. And when it had fallen 40 meters from the top, it means it was actually 10 meters above the ground. So when it was 10 meters above the ground, we had already calculated the gravitational potential energy at that point. And we calculated it here in 5.3.3, where we said the mass is 2 kilograms, gravitational acceleration is 9.8, and the height is 10. And we find that it gave us 196 joules. Then all of that gave us 196 joules plus gravitational, your kinetic energy, it's half multiplied by the mass, which is 2 multiplied by v squared, which is the speed when it had fallen 40 meters, which we do not know. Then you get a mark again for the substitution there and a mark for the substitution, and Obviously, we also know that we will be getting a mark for the formula. You do your mathematics. Firstly, remember you will get v squared. But you are not solving for v squared, so you must take the square root. And when you take the square root of v squared and the value of v squared, and you take its square root as well, then you will get 28 meters per second. Again, remember the mark is for the magnitude with the correct unit. Now, this is what I am encouraging you to use. But you could have said, at that particular point, right, the change in kinetic energy that the object actually has, it's 980 minus 196 altogether, right? Because as the object is going downwards, remember now the gravitational potential energy is being transformed into kinetic energy, and hence 980 minus 196 represents that change in kinetic energy, right? And that change in kinetic energy, it's actually the kinetic energy at that particular point, right? And then that will be equal to half multiplied by the mass, which is 2 multiplied by v squared, and then the value of v will be 28 meters per second. So that will still be 4 marks. Right. Now, let us look at a different question altogether. Now, here we have an electrician working on an electric pole and dropped his hammer of mass 0.56 kilograms at a height of 8 meters above the ground. Assume that the system is isolated. So when they tell us the system is isolated, we become very happy. Dropped his hammer. Remember, when we drop, it means our speed must be 0 meters per second from where we are dropping. Then the hammer, we've been given the mass. We are very happy that the mass is in kilograms. We are told that it was at a height of 8 meters. So we are happy because our height is also in meters. You see there, my dear learners, you are required to define the term kinetic energy. And we've already talked about that. And I told you that it is a very important definition, right? And as given, I told you kinetic energy is the energy an object possesses due to its motion. And we can see it is 2 marks or nothing. It means we can't give you a mark for the definition being partially correct. The definition has to be entirely correct, and basically those critical words must be there, and you are going to get 2 marks for that. Then you are required to state the principle of conservation of mechanical energy in words. Again, the emphasis is in words. And I know by now you are able to do that. And what does it say? It says the total mechanical energy of an isolated system is conserved, or the total mechanical energy of an isolated system remains constant, and that is 2 marks. Right. How did we allocate the mark there? The mark was part marking, first mark there, another mark for the remains constant. But my dear learners, the pattern or the route that we are currently following is that the principle has to be totally correct for you to get your full marks. We are following this pattern where we are actually giving 2 marks or nothing. And I am really emphasizing this because I know that some of you have access to these marking guidelines and you actually think, might be thinking rather that even if I get the first part correct and I'm not getting the second part correct, then I'll be able to score 1 mark. I am addressing that, my dear learners. Remember, we are following in that route where we are giving 2 marks or nothing for our definitions. So remember that. So it's a principle that you must be able to apply and be able to state. Then we are required to calculate the mechanical energy of the hammer at 8 meters above the ground. Now, let us actually remember what mechanical energy is. And we say mechanical energy is the sum of the gravitational potential energy and kinetic energy of an object. So it is the sum of the gravitational potential energy and the kinetic energy of an object. In other words, my dear learners, you will not be able to calculate the mechanical energy if you are not able to calculate the gravitational potential energy as well as the kinetic energy. You must be able to calculate those, and then you will then be able to calculate the mechanical energy. In other words, we must then know what the potential energy of the object was when it was 8 meters above the ground, and we must know what the kinetic energy was. Now, we are definitely sure that the object had some gravitational potential energy. Why? Because it had a mass, it had G, and it had a height because it was 8 meters above the ground. But in terms of kinetic energy, when it was 8 meters above the ground, we will definitely say that the object's kinetic energy was 0. Why? Because the object was not in, was actually dropped. So the speed was 0 meters per second. So to calculate the mechanical energy, we will say mechanical energy, and it was the mechanical energy at the top, is the sum of the gravitational potential energy and the kinetic energy of an object. So any formula written in this fashion will be allocated a mark. Then remember, we are calculating mechanical energy, so it will be equal to gravitational potential energy. Remember, gravitational potential energy is given by mgh. So the mass was 0.56 kilograms. Gravitational acceleration was 9.8 meters per second squared. And the height, remember, it was 8 meters above the ground. So it will be 8 plus kinetic energy. Remember, it is given as half mv squared. So it will be half multiplied by the mass, which is 0.56 kilograms, multiplied by the speed at the top. Remember, it was 0 because it was dropped. So this entire substitution being correct gets a mark. If you make a mistake, my dear learners, anywhere here, you will forfeit a mark for substitution, and then you will definitely forfeit a mark for your final answer. So you do your mathematics there, and you will find that it gives you 43.90 joules. And it has to be joules because mechanical energy is still your energy. Right. Then we go to 4.1.4. We are then asked to calculate the velocity of the hammer at a height of 3.5 meters above the ground. Now, here we can actually apply the principle of conservation of mechanical energy. To calculate that velocity. Why can we use that? Because we've been told that the system is isolated, and we know that the principle of conservation of mechanical energy, you can only apply it when the system is isolated. If the system is not isolated, you cannot apply the principle of conservation of mechanical energy. So for this one, we are definitely sure we can apply the principle of conservation of mechanical energy because we've been told that the system is isolated altogether. Now, let's just put this quickly in a diagram. Right. So, let's say this is the ground. This is the top. Okay, that one doesn't look nice. I hope you are not laughing at my handwriting. Okay, right, let's get our pen back. Good, there we go. There we go. Right, let us say this is the top of the pole. So if this is the top of the pole, we know from here up to there, it's definitely 8 meters. Now, it is being dropped. So it goes down, it goes down, it goes down, and it will reach this particular point, right? The hammer will reach this particular point. And this particular point, we've been told that it is 3,5. Right, let's fix that quickly. Get our pen back. Right, so we know that this position is 3,5 meters above the ground. So just for interest's sake, what does this tell you? It tells you that they are actually asking us when it had fallen for 4,5 meters. Right. So when it had fallen for 4,5 meters, it means it will be at this position. But now, this position, we then know that it is definitely from the ground up to where it is 3,5 meters. So we must calculate the velocity there. Now, how are we going to do that? We'll use the principle of conservation of mechanical energy. And we are definitely going for option number 1. How are we going to put that? We know that the mechanical energy, when it is 3,5 meters above the ground, will be equal to the mechanical energy at the top. Now, mechanical energy at the top, which one is that? That is when it is at 8 meters above the ground from the point where it was dropped. Then we know that mechanical energy is the sum of the gravitational potential energy and the kinetic energy. So that is when it is still at 3,5 meters above the ground, and then the mechanical energy it's still at 8 meters above the ground. So there was actually no need to break it down because this value, we actually calculated it there. the breakdown was actually done in 4.1.3. Then we do our substitution of the formula. We know EP is mgh, we know EK it's EK, and we also know that it is broken down, it's half mv squared, right? Then that's EK, and that will still be equal to the top. Then for mgh, we will say the mass is 0.56, our gravitational acceleration is 9.8, and the height at that point, it was 3 meters, 3.5 meters above the ground, plus the kinetic energy, and that will be equal to 43.90. This is the mechanical energy at the top. Remember, it is this value that we calculated there in the previous question. Then to get the kinetic energy, we know that kinetic energy is equal to 24.696 joules. So what do we know now? We know the kinetic energy when the object was 3.5 meters above the ground. Then we go further with our calculation. We know that kinetic energy is half multiplied by the mass multiplied by the velocity squared, or basically the speed squared. Just that the question said we must calculate the velocity, but there it's actually the velocity that we are looking for. It's equal to 24.696 because it is the kinetic energy. Then we do our substitution. It's half multiplied by the mass, it's 0.56 multiplied by v squared. It's equal to 24.696. You do your mathematics, you get v squared first. After v squared, you take the square root of the v squared and the value of the magnitude of v squared, and then you find that your answer gives you 9.39 meters per second. So there's our first mark for the formula, for the substitution again for kinetic energy, and for the final answer with units. Now, another learner could have just done it straight away and said the mechanical energy at this point, which is 3.5 meters above the ground, is the same as the mechanical energy at the top when it was 8 meters above the ground. Then we know again mechanical energy is gravitational potential energy plus kinetic energy at that point. It's exactly equal to the mechanical energy at the top. Then EP, it's still mgh, and then EK, it's half mv squared altogether, right? So this is basically a repetition there, but this is half mv squared, which is your EK at 3.5 meters above the ground is the same as the mechanical energy at the top. For mass, you substitute it, 0.56 kilograms, G 9.8, H 3.5 meters plus half multiplied by the mass, which is 0.56 multiplied by v squared. It's equal to the mechanical energy at the top, which is that value there. And then you do your mathematics and you find 9.39 meters per second. So 1 mark for the correct formula, 1 mark for that entire substitution, 1 mark for the mechanical energy at the top, and 1 mark for the final answer. So that is how you would have answered that particular question altogether. Then we go to question 4.1.5. It is saying, give the magnitude of the hammer's kinetic energy just before it hits the ground without calculations. In other words, give us that value of the kinetic energy, but without calculations. In other words, you don't have to perform a calculation in order for you to give us the value of the kinetic energy. Now, how will we do that one? Remember, the system is isolated to start with, and that is where our clue is. Now, just before it hits the ground, it's actually right at the bottom. So we know that the mechanical energy at the top is equal to the mechanical energy at the bottom. Now, if the mechanical energy at the top is equal to the mechanical energy at the bottom, now, by knowing that at the top, the potential energy is a maximum and the kinetic energy is 0. And again, knowing that at the bottom, the kinetic energy is a maximum and the potential energy is 0. It tells us that all of the potential energy that the object had at the top was converted to kinetic energy at the bottom. So all of the gravitational potential energy at the top, when the object was now on the ground, or just before it hits the ground, was all converted into gravitational potential energy. And therefore, if all of the gravitational potential energy at the top was converted into kinetic energy just before the object hits the ground, it means the value of the gravitational potential energy at the top must be equal to the value of the kinetic energy at the bottom. And therefore, our answer there will be that the value of the EP at the top must be equal to the value of the EK just before the object hits the ground. And we found that the value was for the potential energy at the top, it was actually 43,90 joules, right? Because this was 0, so it was 43,90 joules. And that then tells me that the kinetic energy must be 43,90 joules as well. And why is that the case? Because the system is isolated altogether. And if the system is isolated, then the total mechanical energy is conserved. Are we clear? So the mechanical energy at the top is equal to the mechanical energy at the bottom. So how would we phrase that to get all the marks? We are saying the kinetic energy is 43,90 joules. And what is our reason? The system is isolated. We get the first mark. And if we say the system is isolated, then it implies the kinetic energy at the bottom, meaning just before it hits the ground, is equal to the gravitational potential energy at the top. And that's where you will get your second mark. Or another learner could have said the mechanical energy is conserved because the system is isolated. Are we clear? And that then sums up our questions from question 4.1.1 up to question 4.1.5. Right. I hope you are doing well and you are still following. Now, let us go to question 4.2. Now, 4.2, it's still a question on this particular topic, work, energy, and power. And it focuses more on work. And that is what we also need to remind ourselves of, because our questions are going to have a lot of work problems. Now, a man applies a force of 200 newtons to pull a crate full of bricks over a distance of 9 meters. The total mass of the crate with its contents is 120 kilograms. So there we can see that the force there, it's an applied force, is 200 newtons. So we are happy it is in SI units. And it was pulled over a distance of 9 meters. Remember now, the distance that it was pulled actually is equivalent to the displacement, which is delta x. Then the total mass of the crate with its contents is 120 kilograms. So that represents the mass, and we are happy because it is in kilograms. Then we are given a diagram here. Now in this particular diagram, there is something that I want you to see. We've been shown the magnitude of the applied force to be 200 newtons, the displacement to be 9 meters. But can you see that we have been shown the value of the frictional force? And this shows me that you need to be able to then read what has been given to you and also look at the diagram. So you can't just read and not look at the diagram, but you also can't just look at the diagram and not read. So you must be able to do both. Now, in 4.2.1, we are required to define the term work done. Now, work done is actually work. And we know that work is the product of the applied force on the object and the displacement in the direction of the force. And how do we remember that definition? Remember, when you just look at the formula for work, W is equal to F delta X multiplied by the cos of theta. We can see when we want work, we are getting the product of the force applied on an object and the displacement in the direction of the force. So that is 2 marks. Let us see how we mark that. Work done is the product of the force applied on an object and the displacement. First mark in the direction of the force. Again, I will repeat, remember, we are following that pattern where we actually give 2 marks for everything or nothing. So actually, remember, all of this is important and you will get all your marks. Then, we are required to then, in 4.2.2, calculate the amount of work done by friction. So if we want the work that is done by friction, then we are going to use a formula for work because we want the work done by the frictional force. And we can see that the magnitude of the frictional force is 40 newtons. Now, our object, we can see according to the diagram, it is being displaced to the right-hand side. Now, if it is being displaced to the right-hand side, it means the direction of motion is to the right-hand side. Now, frictional force by nature is a force that opposes the direction of motion of an object and acts parallel to the surface. So it means it is acting to the left. Now, if I have to then substitute the value for theta, I know that if it goes in a completely opposite direction, then the angle must be 180 degrees because this is the direction of displacement and this is the direction of the force. And the theta, we know it is the angle between the force in question and the direction of displacement. And we know that will give us 180 degrees. So let us calculate the work done by the frictional force. So the work done by the frictional force will be given by that formula, which will then be the frictional force multiplied by delta S multiplied by the cos of theta. Then the work done by the frictional force will be the magnitude of the frictional force multiplied by the displacement, which is delta X multiplied by the cos of theta, which is 180 degrees. Then the magnitude of the frictional force we were given, it's 40. The displacement of the object is 9 meters. Our theta is 180 degrees, which equates to -1. Now, even if you just left it there as the cos of 180 degrees, that is 100% correct. And we get -360 joules. Now, that's the 3 marks. Now, what you should be able to see there is that we have written the negative there altogether. We have written the negative there. It is compulsory for you to show us the negative. Why? Because the frictional force is doing negative work. And remember, when it does negative work, actually, the effect of that is that it then decreases the kinetic energy of an object. Right. So it's doing negative work. Now, let us go to 4.2.3. What should be the size of the angle between the applied force and the direction of motion for the amount of work done on the crate and its contents to become 0? Now, we are specifically referring here to the applied force. Now, which angle should this applied force act at in order for it to give us a work of 0 joules? Now, let's see this. Let's say we want to see how we can get to a work of 0 joules. Right? To get to a work of 0 joules, then this value of theta, it must be 90 degrees, because you will take the magnitude of the applied force, which is 200, you will multiply it by the displacement, which is 9 meters. That one doesn't look nice. And we will multiply that by the cos of 90 degrees. Just make the slide quite neat for you. Right. Once that angle is 90 degrees, then we are going to get a work of 0 joules. Now, how do we get to 90 degrees? It means then the applied force would have to be sometimes I'm really good with my pen and sometimes I'm not that good with my pen. Right. If the applied force was going upwards and the direction of displacement was to the right, then you would actually get an angle of 90 degrees, because the value of theta is the angle between the force in question and the direction of displacement. Then you would get 90, and the cos of 90 is actually 0, and then the work will be 0 joules. So our answer there would then be 90 degrees. And remember, the degree sign must be there. And that's something that you definitely omit, so you will be penalized. Then we must calculate the net work done on the crate and its contents. Now, if I want the work done on the crate and its contents, then I must sum up the work done by all the forces that are acting on the object. Now, You can't do the net work done on an object if you don't know the forces that are acting on an object. So let us make things easy for ourselves and actually draw a free body diagram. Right. The crate is on a surface, so we have an upward force, which is the normal force. We have a force, just making it nice. We have a force that goes downwards. And that force, we definitely know that it is the force of gravity. And then we have an applied force F applied, which can be represented as FA, and then we have the frictional force. Now, is the force of gravity doing work? Our answer is no. Why? Because it is going down, and it is going down, and the direction of displacement is to the right, so we get an angle of 90 degrees. So it is not doing any work. Then is the normal doing work? No, the normal force is going up. The direction of displacement is to the right, so it's not doing any work. So this force and that force, they are not doing work. But the applied force is doing work. The frictional force is doing work. In other words, if I want the net work done, it will be the work done by the frictional force plus the work done by the applied force, because the normal force and the force of gravity are not doing any work. So how do we calculate that? Best option there, option number 2. There we just say the net work done on an object is the work done by the frictional force plus the work done by the applied force. Then you know the work done by frictional force will be represented by frictional force multiplied by delta x cos of theta. And we know the frictional force acts at 180 degrees. Plus the work done by the applied force will be applied force multiplied by delta x multiplied by the cos of 0 degrees. Why 0 degrees? Because the object is going to the right, it's displaced to the right, and the applied force is acting to the right, so there is no angle between them. Then you do your substitutions. Your frictional force is 40, your delta x, it's 9 meters. The cos of 180 degrees, it's -1. And I told you this is not compulsory, even if you just left that as cos of 180. Then we get a mark there. The first mark was also there on the formula. Plus the applied force, it's 200 newtons multiplied by delta x, which is 9 meters, multiplied by the cos of 0 degrees, which is 1 mark. Which is 1. So the cos of 0 is a 1. So you can still leave it as cos of 0 degrees. And you do your mathematics, that will give you a net work of 1,440 joules. So that will be a mark. Remember, it must be in joules. Converting it to kilojoules, it's really not necessary unless if we tell you to take it to kilojoules. But the mark is for when you give us in joules. What else could I have done? Option 3, it's also a nice option. Why? Because we want to first calculate the net force. After we calculate the net force, then we can go into a second formula which calculates work net and requires us to substitute the F net altogether. So to calculate the net force, we say net force, remember, is the vector sum of all the forces that are acting on an object. So the normal force and the force of gravity, indeed, they are acting on the object. But now, the object is not going up and down. The crate is not going up and down. And if the crate is not going up and down, what does that tell me? It tells me that the vertical forces are balanced. The vertical forces are in equilibrium and they're giving me a net force of 0. And therefore, I don't have to include them into my calculation of the net force. But the forces that are acting horizontally, which is the applied force and the frictional force, they are not balanced. And because they are not balanced, then they will give me a net force that is greater than 0. And hence, I have to include them on this particular formula to calculate net force. Then, in this one, let us say we choose to the right to be positive. If we choose to the right as positive, then it means the left is going to be negative. Then the applied force is 200 newtons plus the frictional force. Remember now the frictional force is going to the left, so it will be negative 40. So we get the net force of 160 newtons. And this net force, we definitely know that it is to the right. How do we know that it is to the right? Because we got a positive value. Then we go to our formula sheet. We will get the formula W net is F net delta X cos of theta. Then the net force is 160, the displacement is 9, multiplied by the cos of 0 degrees. Why 0? Because the net force is to the right and the object is displaced to the right. Then we get the net work to be 1,440 joules. And that's where we will get a mark. Again, you could have done it in this fashion. This option 3 is actually the same as option 1. It's just that the learner there just indicates that the F net is actually 200 minus 40, which is what we have done there. So it gives you 160. And then after you get 160, then you multiply by the displacement of 9, and the cos of 0 degrees gives you 1, and you get 1,440 joules altogether. It's just that this learner there, or in that method, we are just encompassing the F net into the formula and performing the calculation within. Are we clear? And that sums up the questions from 4.2.1 to 4.2.4. Right. So those are the questions that I had prepared for you, my dear learners. Remember again, for your examination tips, that this question will be plus minus 22 marks. And I want to elaborate further that you will be getting questions on work. You will be getting questions on energy, which is kinetic energy, gravitational potential energy, as well as mechanical energy. And you will be getting questions again that require you to encompass the principle of conservation of mechanical energy. So they are all going to be there. And you must still be able to relate work with energy, and being able to relate energy in terms of how it links with an isolated system, meaning when is mechanical energy conserved and when is mechanical energy not conserved. Furthermore, you must be able to do calculations of power. And we know that power is the rate at which work is done. So we have two formulas that you can use to calculate power, which is power is W over delta T, or that one where power is the force that is being applied by the object, applied on the object rather, multiplied by the average speed of that particular object. Be able to do that. And again, be able to link work with power, because when we calculate power, we say it's the rate at which work is done. So if you are not able to calculate the work that is done, it will be difficult for you to calculate the power. Again, remember, we say power is the rate at which energy is expended. Altogether, work is done or energy is expended. So it is important for you to be able to calculate energy so that you are able to calculate the power that a particular object will have. So it is important for you to be able to link each of these particular concepts with each other. Again, my dear learners, read your questions. Ensure that you use the correct formula on a given calculation, and make sure that you copy the formula from the examination guideline. Again, when we get to the principle of conservation of mechanical energy, remember that principle is only applicable if the system is isolated. Now, how will you know the system is isolated? You need to do some thorough reading in the explanations that we give you, or in the scenario that we give you as we read there, as stated in that particular question at the beginning. And also be able to relate what is written in the text to what you see on the diagram. And don't just look at the text and not look at the diagram. You need to look at both of them, and they must be talking to each other. So be able to work with that. And again, in this topic, my dear learners, it will be very difficult for you to work with them if you are not able to break down a formula. For example, when we deal with mechanical energy, when we deal with questions on mechanical energy, you can know that the mechanical energy at the top is equal to the mechanical energy at the bottom. But then you must be able to see that mechanical energy is the sum of the gravitational potential energy and the kinetic energy. So you must be able to break down a formula altogether. Furthermore, you must be able to give us units and give us correct units as well. So be able to do all of those things, and you are well on your way to excelling on work, energy, and power. I will see you in the next lesson, where we'll be dealing with another topic on technical sciences. Now, thank you very much. I hope you enjoyed the lesson as much as I did, and I wish you all of the best. Thank you very much, and enjoy the rest of the afternoon. Goodbye.